Welcome back, everyone. Today on the deep dive, we're tackling something pretty foundational in quantum mechanics.
Mm.
The idea that complex numbers are absolutely essential. But what if? What if they're just a really useful mathematical tool, not strictly necessary for reality?
Fascinating question, isn't it? We're going to be looking into Pushpendra Singh's work, specifically the paper Real Valued Quantum Computation via the Hilbert Transform in Unified Quantum Mechanics.
Yeah, so our goal here is to explore how this unified quantum mechanics, or UQM, tries to rebuild quantum theory using only real numbers. And, what that tells us about things like entanglement and maybe even some surprising practical uses down the line.
Right. The fundamental issue is that standard quantum mechanics absolutely relies on complex numbers, especially that complex phase term, e to the I phi. It's everywhere.
Crucial for computation, interference, everything.
Exactly. So the question is that I, that imaginary unit, physically real? Or just a convenient calculation trick? We know simple real-only theories don't work. They've been experimentally disproven. So any contender must perfectly match all the results of standard, complex quantum mechanics.
Okay, so how does UQM pull this off? What's the proposed solution?
Well, instead of just throwing out I, UQM replaces its job, its algebraic function, with something else, something physically motivated and, crucially, real valued. It uses the temporal Hilbert transform, which we can call HT.
The Hilbert transform. Okay, I know that from signal processing.
Precisely, and that connection is key. So HT is this real valued operator that lets you rebuild the entire quantum framework using real operator algebra.
So what is the Hilbert transform for those maybe less familiar?
It's fundamentally an integral operator. What that means is its value right now at time t actually depends on the signal's value across all other times. So it has this inherent non-locality baked into it, temporally speaking.
Non-local in time. That sounds significant for quantum mechanics.
It is. And there are a couple of other really key properties. It acts as a perfect 90-degree phase shifter. So if you feed it a cosine wave, for instance, HT turns it into a sine wave.
Okay, like shifting the phase by pi over 2.
Exactly. And the really crucial part, if you apply HT twice, you get the negative of what you started with. So HT squared equals minus the identity operator II.
And that's the link, because I squared equals -1.
That's the core algebraic mimicry. HT2 I perpendicular I2 equals -1. It gives a real physical operation that does the same mathematical job as the imaginary unit.
So you've got this HT operator behaving algebraically like I. How does that let you sort of reconstruct quantum mechanics using only real stuff?
Right, because the algebra you can build using just the identity operator I and this HT, well, it turns out to be mathematically identical. The technical term is isomorphic to the field of complex numbers.
Meaning you can map everything one-to-one.
Essentially, yes, a direct translation.
Yep.
So instead of qubits having complex number coefficients, in UQM they have these real operator coefficients involving I and HT. And the Schrödinger equation, it gets transformed into what Singh calls a unified real wave equation. The I in the standard equation's energy term is directly replaced by HT.
Which makes the equation itself non-local in time, because HT is.
Exactly. And that familiar phase rotation, e to the I phi, gets replaced by a real phase shift operator built from HT. It acts on the real wave functions to produce precisely the same phase shifts we expect.
Wow. Okay, what about measurement? Standard quantum mechanics uses the Born rule with complex amplitudes. How do you get probabilities here?
They derive an analytic Born rule. You basically take the real wave function squared, add the square of its Hilbert transform, and that gives you the probability density. And importantly, this is mathematically proven to be completely equivalent to the standard Born rule. It gives the same answers.
So it reproduces the probabilities correctly. What about gates? Entanglement.
Yeah, handles those too. Many gates, like Poly-X, Z, Hadamard, CNOT, they're already real, so they stay exactly the same.
No change needed.
Right. Others, like the poly-Y gate or phase gates, which normally involve I, are just rewritten by substituting HT for I.
So Y becomes a matrix with HT and HT off the diagonal.
Exactly. And the formalism reproduces entanglement perfectly. It interprets entanglement as this perfect correlation between the system's energy state and how its wave function evolves in time, specifically components evolving exactly 90 degrees out of phase in quadrature.
Okay, so we've seen how UQM manages to replicate standard quantum mechanics using real operators. But let's step back. What are the deeper implications here? What does this mean?
Well, one potentially profound implication relates to that non-locality we mentioned. Because HT is inherently non-local in time, this theory suggests that quantum phase itself might be a fundamentally non-local physical property.
So things like the EPR paradox, spooky action at a distance.
Exactly. This framework sort of reframes those non-local correlations. It ties them directly to this physical mechanism, the non-local Hilbert transform. It almost becomes a signal processing problem, in a way.
That does feel more tangible, maybe. Replacing the abstract I with a concrete physical operation affecting the wave function's time evolution.
It offers a different kind of intuition,
Yeah.
yeah. And it also suggests potentially completely new ways to build quantum hardware
How so?
by connecting quantum logic directly to classical signal processing ideas. You could maybe imagine using things like electro-optic modulators in photonics to directly shape the phase using Hilbert transforms, or engineering specific time domain interactions in superconducting circuits.
Or even using fast digital signal processors, DSPs, because they do Hilbert transforms routinely.
Right, DSPs could potentially perform analog simulations of these real-valued quantum systems. It bridges the gap between abstract theory and concrete engineering in a new way.
And are there implications for quantum algorithms themselves?
Potentially, yes. If you rewrite something like the quantum Fourier transform using HT instead of I, you find it reveals this deeper structural link to the classical fast Fourier transform, the FFT. That might open doors to entirely new classes of maybe quantum signal processing algorithms we haven't thought of yet.
Interesting. Okay, so let's wrap this up. We've explored this deep dive into unified quantum mechanics.
And seen how it provides a complete self-consistent quantum framework using only real numbers and operators by replacing I with the temporal Hilbert transform, HT. And crucially, it's operationally identical to standard complex quantum mechanics.
I think the big takeaway here is pretty startling. The complex nature of quantum theory, as powerful and successful as it is, might not be a fundamental feature of the universe itself. It could be an emergent mathematical structure.
Which leads to that final thought to leave you with. If the universe isn't necessarily built on complex numbers, what other deep mathematical assumptions that we make about physical reality might just be powerful tools rather than fundamental truths? And thinking about quantum mechanics as advanced signal processing, what entirely new engineering paths might that unlock?
Definitely something to mull over. Thanks for joining us on the deep dive.